speaker Leo Tzou from Sydney, and he will be speaking about single point measurement tomography. Thank you, please.
Yeah, thanks for the invitation to speak about my result. And I wish we could all be doing this in Cambridge, but nevertheless, it's yeah, hopefully next year. All right, so as Mati said earlier, nonlinearity really helps with inverse problems, and I'll just rehash what he said a little bit, summarize what he said, is that there is this result by Lassas, Kurylev-Uhlmann, where they were able to measure the local source-to-solution map of the semilinear wave to determine the global conformal Lorentzian structure, at least in a causal diamond. So you have a time-like curve and a space-time cylinder. And by measuring, by allowing yourself sources in this space-time cylinder and then measuring the resulting nonlinear wave in the cylinder, again, you can determine the Lorentzian or conformal structure of the maximal causal diamond. And so this was later improved to the more realistic, physically realistic case of the Einstein equation, where you have sources F1 and F2. And in this case, they start with a background Lorentzian metric, which already satisfies the Einstein equation. And then they flip on the source and measure the perturbations that are caused by these sources, again, in a small space-time cylinder. And then from this information...
Excuse me, I think you are a bit too close to your microphone, and then it makes some noise.
Oh, yeah. Sorry.
That's all right.
Is it better now?
Yes, better, much better.
Yeah. Okay, so and then they were able to, again, by using that measurement, by measuring the small perturbations, they were able to reconstruct the conformal structure of the space of the causal diamond. And this was later improved, not later improved, but Bielhowski and collaborators did use similar ideas to reconstruct the causal, or as Mati said, not just the causal, the conformal structure, but the entire metric by looking at the relativistic Boltzmann equation. And so it turns out that these methods are also useful for recovering lower order geometric structures. As Mati said, you start with a connection wave equation with a connection A, and then you're able to recover the connection A up to gauge equivalence. And in their case, their background geometry is the Minkowski one. And so this sort of gave them an idea on what to do for the Yang-Mills equation. So for the Yang-Mills equation, they were able to do the same thing. Again, the background geometry is the Minkowski metric. So after we have had success in sort of, whenever we have success in solving inverse problems, we become more ambitious and we think about, well, what can we do to solve, what are the partial data problems, or whether or not we can solve partial data problems. So I'll give you an example of partial data inverse problems. So the most famous one that everybody knows about is the full data Calderon problem that was solved by Sylvester-Uhlmann. And this says that the Cauchy data of the Schrödinger operator measured on the entire boundary determines the Schrödinger potential V. And this was improved to the partial data problem by Buchheim-Uhlmann and Koenig-Sjöström-Uhlmann, where they showed that by measuring the Cauchy data of the Schrödinger operator on only a part of the boundary, you can still determine the entire potential V. So the second result is obviously better than the first one, because the second result, you're able to determine the same amount of information by measuring significantly less data. So it is then fair to ask, for these nonlinear interaction inverse problems that we have had so much success in, what are the equivalent partial data problems? And so, as Mati said, there's a version of this where Mati, Lassas, and Oksanen considered the disjoint source to solution measurement. So in some sense, that was a partial data. but I'm going to go in a different direction in what I consider to be partial data here. So the partial data problem that I consider are driven, these questions that I'm considering, are driven by the scarcity of data in mathematical imaging, as with all partial data. So let's look at the example of seismology on Mars, where we have only one seismometer to measure the seismic activity on that planet. And we have to somehow, from this one point data, determine the innards of Mars. And similarly, so Matti mentioned satellites looking at distant galaxies, and we do indeed have a lot of satellites on the ground and in orbits, and they point in different directions. However, you don't have to go very far. So this is just looking at Earth from Saturn. Saturn is not that far away. Before the Earth is nothing more than a single point. So it's only 1.5 light hours away. Right, so all these telescopes that we have are pointing in different directions. They're looking in different directions, but effectively they're looking from the same point in space. So these questions motivates us to ask, well, how much information can we determine from data collected at just a single point? And so inverse problems tends to be solved on open sets. So because mostly analysts work on them, and analysts like open sets. So the inverse problems as we know them is that you're given data on a small open subset, and from this information you deduce some kind of a global geometric analytical structure. And the fact that the operative word here is the word open, because once you have an open subset, you have data collected at infinitely many points. So let's look at some of my favorite geometric inverse problems. So for example, this one by Lassas-Uhlmann, where the behavior of harmonic functions on a small open subset of the boundary, the Cauchy data, determine the global structure of the Riemann surface. And I mentioned this result by Koenig, Schuster, and Uhlmann earlier, where the Cauchy data measured on a small open subset of the boundary determined the entire Schrödinger potential V. And as Matti mentioned, these nonlinear source-to-solution map for the semilinear wave equation measured in an open space-time cylinder determines the conformal structure of the causal diamond. So let's contrast these results to the one that I'm about to present, which is the single point data inverse problem, where we measure the source-to-solution map of the semilinear wave at only a single point, and from that we determine the global structure of an entire Riemannian manifold, or up to, of course, the propagation speed of light. Right, so it depends on how long I measure, how much time I measure. So let's start with the geometric setup. So I have a Riemannian 3 manifold, which I represent by just the schematic diagram being two-dimensional. And I have a fixed point x0 on that Riemannian manifold, which I will call the observer, and that's in blue. And there is a small open patch, which is a yellow dot here, which I call U, which is an open subset containing x0. The reason why my schematic diagram is two-dimensional is because I need my vertical axis to be the time axis. So the world line of my observer x0 is then this vertical axis, the blue vertical axis. And that open set U is just this space-time cylinder in yellow. And I can make my Riemannian metric into a Lorentzian metric by simply adding minus dt squared to it. So I think the people who do wave equation call these Lorentzian metrics ultrastatic. And from this, we have a wave operator box. All right, so this is just the standard wave operator in Riemannian geometry. Okay, so So now what I'm going to do is I'm going to have some sources that are only contained in this, this yellow cylinder, and I'm going to turn them on, and they're going to produce waves that are supported in their causal light cone. And of course, I cannot measure these waves everywhere because there's only a single observer stuck at a stationary point x0. So you can only measure these waves along this vertical axis. Right, so now the PDE setup is that for each source f, which is sufficiently smooth but not infinitely smooth, that is compactly supported in this space-time cylinder, this yellow cylinder, and if it's small, we can solve the semilinear wave equation box u plus u cubed is equal to f. And we define the single observer source to solution data by simply taking the source f and you map it to the function u restricted to that single point, right? So this is where it's different from what has been done before. Before, the source to solution map is you restrict the solution u back to that yellow cylinder. Here I'm only restricting it to the point x0, but for all time. I can restrict this finite time if I want, but then I only recover a Riemannian ball rather than the entire Riemannian structure. So the result here is that this measurement determines the topological, differential, and Riemannian structure of the entire Riemannian manifold. All right, so let's look at how we go about proving this result, and then strategy is, of course, due to Lassas-Kurylev-Uhlmann. And because I'm looking at the cubic three-plane interaction, as Matti said, I should also mention that this is partially inspired by Chen, Lassas, Oksanen, and Paternan's work. So because now L here is L here is the analytic data that you obtain from measuring semilinear wave equations, and we're trying to recover from that some geometric structure, which is the Riemannian structure of Mg. So for that, we need a bridge between the analysis and the geometry. And of course, this bridge is given to you by the propagation of wavefront, which says that if you only look at the linear wave equation, box u is equal to f, then the wavefront set of u are the Hamiltonian flowouts of the like wavefront sets of f. So for example, here I have a source f with a singular support at that point, and it has this direction as wavefront set. Then if I solve the wave equation, this entire wavefront set will propagate in u along a light geodesic. All right, so now how do we use this idea to solve our inverse problem? Well, the idea is, of course, this nonlinear interaction method invented by Lassas-Kurylev and Uhlmann, where if I have two sources, f and f prime, and they have their respective wavefront sets pointing in various directions, and I turn them on, and these wavefront sets are going to, or the singularity is going to propagate, and I aim them at the beginning so that they're judiciously chosen so they collide. And because I need three wave interaction, I have an auxiliary source just so that I have three waves. And because I have a nonlinearity u cubed, these three waves are actually going to interact to sort of manufacture a new wavefront set, which will then echo back to the observer. Then the observer along that world line, staying at a fixed point x0, is going to observe this singularity. Right, so now let's look at in more detail how this idea specifically helps me in my particular case. All right, so here is my, this is an even simpler schematic diagram where the entire three-dimensional Riemannian manifold is just a line. And my fixed observer x0 is that blue point, and the open neighborhood u is that yellow patch there. And I consider the space-time diagram, so the vertical axis is now the time axis. So I will place the source at time is equal to 0 at my observer point x0. And at any other point x in my set U, in my open set U, I'm going to place another source at another time, let's call that t. And they will be arranged in such a way that the geodesics coming out of these two points, out of these two sources, will collide at some point y, which I don't know where, and at some time, which I don't know what time. And the green line there is, again, just an auxiliary wave because I just need 3 waves interacting rather than just 2. All right, so as I said before, this is going to produce an echo bouncing back, and the observer is going to observe this wave at the point x0, that's where the fixed observer is, and at some time, which I will call 2t0. Right, so this is where the singularity is going to get observed. And so let's look at, so because the Riemannian manifold is time independent, this wave coming back from y to x0 is going to be simply the wave going out from x0 to y, but running backwards. Except, of course, time always sort of progresses forward, right? So, but these two trajectories on the Riemannian manifold are just reverses of each other. So therefore, I know that it took time 2t0 to go from the point x0 to out to some point y and then bounce back along the same trajectory. So I then must be able to conclude that the collision of the 3 waves happened at time t0. Now let's look at this point x, the source which I placed at spatial point x and at time t. Then I know because the collision happened at time t0, I'm able to deduce that it must have taken time t0 minus t to go from x to y. So therefore, the upshot is that the distance from this point x to this unknown point y is t0 minus t. So from this information, I'm able to deduce the distance between every point in x in the yellow set U and any point y anywhere out there. And so this allows me to conclude that if the two manifolds, M1 and M1G1 and M2G2, so these are 2 a priori different Riemannian manifolds, that share a common point, which I call x, which is the fixed observer, and they share a common open set U, and you can always, of course, arrange for this. Then for all y1 in the first Riemannian manifold, there exists a unique y2 in the second Riemannian manifold, such that the distance between x and y1 measured in the metric g1 is equal to the distance between x and y2 measured with respect to the distance g2. And you can conclude this only for all x in this small neighborhood U that is shared between the two manifolds. But this is true for all y1 and y2. And you can, of course, deduce the converse statement is that for all y2 in M, there exists a unique point y1 such that this is satisfied as well. So what this allows you to do is you can define a map. It's actually a bijection of this condition. And so this map is from a set theoretical point of view is very nice. It's a bijection, but topologically it could be non-differentiable. It could even be discontinuous, right? This map. So let's look at how I can show that this map here is actually a smooth map. So let me stop sharing my PDF and let me share my web browser. All right, so here's the 2-dimensional Riemannian manifold picture, in Euclid picture, but this sort of a schematic, again, it's a schematic. Right, so x1 and xu, I have a chat. X1 and x2 are these 2 points that I'm allowed to wiggle in a small neighborhood. And here's a point y. And you see these 2 numbers here, the blue number and the red number. These are just simply distances from the point x1 to y and x2 to y. right? So then, so these two, the distances actually gives you a coordinate as you wiggle y. And now the only problem when this is only where this is a problem is when these two things overlap like that. But then since I'm allowed to wiggle x1, x2, I just put this wiggle x2 a little bit, then again I get another nice local coordinate system here. So now if we go back to slides. So because of this fact right here, psi is nothing more than the identity map when you pull back by those two the coordinate system that I described. Right, so now you can conclude that psi is actually a smooth map, and its bijection and its inverse is smooth, and therefore it's a diffeomorphism between the two Riemannian manifolds. All right, now and to recover the metric, let's look at this picture again. So here we have a point y. Now I just need to wiggle x2. Let's just look at x2, right? So I'm allowed to wiggle x2. So therefore, by wiggling x2, I can actually determine by combining an argument using Gauss's lemma, a small portion of the unit sphere I. Right, and of course, the Riemannian metric, the unit sphere is uniquely determined by a small portion of the sphere, and therefore I have myself that psi is an isomer. All right, so let's go back to my slide. Okay, so now as this is analysis, so there's always complications. You can always count on analysis to ruin a nice geometric argument. And the problem here is that, as you all know, the light ray coming from these sources are not these nice clean light rays that I drew. They're not nice like this, so this is not an honest picture. But they're actually projected Lagrangians. Right, so let's look at a more honest picture where my internet is unstable again, so please let me know if I'm dropping out in sound. So downstairs is in this box is a honest picture of what happens in R3 as time progresses. So downstairs in the box is the movie, and upstairs in the space-time diagram is a schematic diagram of what's going on downstairs in space-time. Right, so as time progresses, these plane waves will move forward, will propagate, and so at first you have just a double interaction of waves, and eventually you will have the triple interaction, and the intersection of three distorted plane waves is along a curve. So that point that I drew up here, K, is actually a space-like curve in your space-time, right, rather than a single point. And now the flow out that I drew, or the ray coming back from this K, is not as clean as that I've drawn it, but rather the entire flow out of the conormal bundle of the space-like curve. Right, so that's what the kind of picture that's sort of honestly happening, and this is downstairs is the movie again, so it propagates out like that. And so let's look at what can happen when you have this flow out Lagrangian and a distribution that's associated with this flow out Lagrangian from a space-like curve. Right, so here is a space-like curve in 1 plus 2. Right, so now the vertical axis again is the time, and let's look at the flow out, or the light-like flow out from this space-like curve. So it's everything everywhere is pretty nice and co-normal, except for at that focal point where it fails to be co-normal. So if my observer is this vertical line that intersects this Lagrangian distribution where it is conormal, then the restriction of this Lagrangian distribution to this vertical time-like curve would respect the fact that there are singularities. So you would be able to see the singularities of this Lagrangian distribution in the restriction to that blue line. However, if the observer is unlucky and it happens to intersect this projected Lagrangian exactly at that focal point, the observer may not see the singularity. So since my entire method relies on the fact I'm able to see singularities, this is obviously a big problem, right? So I may be missing singularities here and there. And the solution to this is introduce what I would call microlocal mirrors. So this is where you look at this distribution, which is mostly conormal, and you look at a conormal part of it that is near that focal point, and you put an additional source there, so this would require one more level of nonlinear interaction. And where that Lagrangian distribution is conormal, it will interact with this conormal, orange conormal source, and that would produce a wave coming back. And because you're very close to that observer, everything that you care about is conormal. So you can then observe that singularity coming back to you from this additional level of interaction. And now by taking this source, taking this orange additional source closer and closer to that focal point, you're able to deduce that the focal point is in the singular support of the original Lagrangian distribution. So in order to pull this trick, I need the fact that I'm able to produce these types of interactions, arbitrary conormal type interactions, arbitrarily close to that focal point. And the lemma that makes this work is that if you have 2 points x, y that are on your Riemannian manifold, and they can be joined by a geodesic segment that is strictly contained in a unique minimizing curve. So here are 2 points, and you look at the minimizing curve. They can both be extended slightly and still be minimizing. And let t0 be the distance between these two curves, these 2 points. So that's the length of that line segment between y or curve segment between y and x. And let 0y space-like curve on r times m. So here's the picture. So here you have the point y and at time 0, and here you have the point x at time t0, which is the distance between these 2 points. And you have a space-like curve k, which contains that point 0y in space-time. And you call L the light-like flow-out from the conormal bundle of k. It looks like something like this. Or the projection looks something like that. Then there is a sequence of points in space-time that are on the projection of Lagrangian, converging to the point t0x. So let me draw a picture. So here's a sequence of points in red that gets ever closer to that point t0x, such that there are open sets Oj containing each point on the sequence, satisfying that essentially the Lagrangian is conormal in this open neighborhood. All right, so here's a point on that sequence, and you can find a small neighborhood Oj such that if you only look in there, everything is conormal. All right, so this allows us to pull off this argument where each interaction is going to take place along that sequence where things are conormal, and then you're able to do this trick. All right, so the thing is that this difficulty actually motivated us to sort of develop this machinery, and it turns out that this machinery gives us a very robust way to deal with future more general things than just a ultrastatic Lorentzian manifold. Sorry. Let me just, sorry. So I need to go a little bit further, sorry. So the fivefold nonlinear action, so up to this point, I haven't talked about any PDE yet, so I'm going to actually show you what happens at the level of PDE for these 10. Right, so let F1, F2, up to F5 be sources that are chosen later, and let F be the sum of these sources. And let's look at the solution box U plus U cubed is equal to F, and look at the first linearization, UJ to be the first linearization, UJK be the second linearization with the J and K, etc. So box UJ is equal to FJ, and box U1, 2, 3 is the linear action of the U1, U2, and U3. And box U1, 2, 3, 4, 5 is the linear action U1, 2, 3, and the interaction of U4 and U5 plus other things. Right, so that's the analytic setup. And I will show you what happens to these things in picture. Right, so let Fj be sources, micro-localized judicially in a neighborhood of chosen points, in a conic neighborhood of chosen points. And you're going to propagate them. Box Uj is equal to Fj, and you're going to propagate them. And the flow out, or the projected flow out are these like hypersurfaces, at least before you hit conjugate points. And as we said earlier, they're going to intersect along the triple intersection of these three projected Lagrangian is actually going to be K, some space-like curve, which I will draw there. That's K. And then U1, 2, 3 will be the flow out from the conormal bundle of this K, which looks like this. And now let's zoom in here to U1, 2, 3, near where U1, 2, 3 intersects my observer in blue. So now I know that I have a sequence, Tj, Xj, along this projected Lagrangian that converges to where U1, 2, 3 intersects the vertical line, which is the word line of the observer. So I'm going to choose my source F4 such that U4, the solution of box U4 is equal to F4, is nothing more than a vertical line, right? So this is, or at least a conormal distribution, a distribution which is conormal to this orange line. And I'm going to choose F5 so that U5 is nothing more than a compactly supported thing that is localized near where this intersection happens. And since U1, 2, 3, 4, 5, or box U1, 2, 3, 4, 5 is the interaction between U1, 2, 3 and U4 and U5, the flow out, or the U1, 2, 3, 4, 5 is a Lagrangian distribution associated to this Lagrangian, or this is the projection of the Lagrangian that's associated to it. Right, and because this interaction between the orange conormal distribution and U1, 2, 3, 4, 1, 2, 3 is very close to my observer, everything is going to be conormal. And so you can always observe conormal things by restricting. All right, so this is the global picture of what's happening, right? So there's just one extra level of interaction that gets around this focal point issue. All right, so it turns out that sort of this difficulty is actually a blessing in disguise, because this machinery allows us to gives us the motivation to actually do bigger and better things. Namely, we want to be able to do general Lorentzian metrics, and this is something that Lowry and I have been discussing. Right, so this is the original Lassas-Kurylev-Uhlmann setup, where you have a globally hyperbolic Lorentzian manifold, and you have a time-like curve contained in some open space-time cylinder. And what they did is they defined a source-solution map, which takes your source, F, and you map it to the restriction of the solution to this space-time cylinder. And so what I'm going to do is, instead of restricting to a open space-time cylinder, I'm just going to look at the pullback of the solution UF along this time-like curve. Right, so the Riemannian strategy is that we have some kind of a wave data, and then we use that to generate some kind of Riemannian distance data, and using this argument of circles and coordinate charts, I get myself an isometry. This is obviously not going to work in the general Riemannian case because your general Lorentzian case, because your Riemannian metric is going to be time evolving, so there's not going to be a fixed Riemannian distance that I could hang on to. So instead of looking at the Riemannian distance data, as Matti said, we're going to look at the 3-to-1 scattering data, and this is exactly what Matti introduced in his talk. Right, so so this is idea given by Faiz Mohammadi and Lassas and Uhlmann. Right, so they say that a subset R, that is a subset of the 4 tuple of the light-like conormal future pointing conormal bundle of your space-time cylinder, is called a 3-to-1 scattering relation if it satisfies the following condition, right? So this is very abstract. Any subset of this 4 tuple that satisfies the following 2 conditions that I'm going to list is going to be called a 3-to-1 scattering relation. Right, so rule number 1, right? So this is a necessary condition. If something is in here, then the light-like flow out, or the light-like path-oriented flow out from Z0 is going to intersect the future pointing light-like flow out from Z1, Z1, Z2, and Z3. So that's the picture here. You have Z1, Z2, Z3 in the past and Z0 in the future. And the future flow out of 1, 2, 3 is going to intersect the past flow out of Z0. And now let's go to a sufficient condition. This is a little bit more complicated. So suppose you have distinct flowouts for 0, 1, 2, and 3, and you have a point that is contained in the intersection between the past flowout of Z0 and the future flowout of 1, 2, 3. So here's the picture. So future flowout of 1, 2, 3 intersect at point Y, and which also intersect the past flowout on Z0. And furthermore, assume that these light rays can be extended slightly without creating cut points. So when Z1, Z2, and Z3 arrive at Y, they're going to be pointing in various directions, eta 1, eta 2, and eta 3 respectively. And you want the covector pointing towards Z0 to be in the span of 1, 2, and 3, eta 1, 2, and 3. Then, if all these conditions are satisfied, then you can conclude that Z0, Z1, Z2, and Z3 is in this 3-to-1 relation. All right, so this is a very abstract idea, but as Matti said, this actually can determine the entire conformal structure of the causal diamond. Right, so now this is our proposition. This is in progress. The single observer sources solution map characterizes a 3-to-1 scattering relation. So as Matti said, I can just use the result as a black box by simply bootstrapping my hyperbolic equation to it. So let's see how we do this. So now my Lorentzian manifold is, because it's globally hyperbolic, it has this product structure R times M prime, except the only difference is that now my Riemannian metric is going to be time evolving, and I will write my every point in space-time x, so x is now a point in space-time as its time component and its x prime component. So if I have a point in the space-time cylinder, there exists a unique covector, a light-like covector that's future pointing, so that the flow out from this in this direction from this point intersects my observer prior to a cut point. Right, so here is my point x, and there exists a unique direction over this point, so that the light-like flowouts intersect the world line of my observer before it hits a cut point. So I'll call that z mu. Now, for any given z0 over this point, you can find a unique covector that is co-normal to the vertical line through this point, such that z mu is equal to z0 plus nu of Z0. All right, so here's the picture. So for any point Z0, I can find, and if I look at the conormal bundle to this vertical line, I can find a covector in that conormal bundle, a unique covector in that conormal bundle, such that Z mu is the sum of Z0 with this orange vector, nu Z naught. So now let's look at, so now given 4 points in this 4 tuple, given a 4 tuple, let the source 1, 2, 3 be point sources localized but near Z1, Z2, and Z3. So that's what it looks like. So you have your sources localized in certain directions. And then, as I said earlier, you're going to have generate this kind of interaction. And U1, 2, 3 will be this flow-out Lagrangian from this space-like curve. And now let's look at this covector Z0. So let Z0 be over the point X, and we construct F4 so that the solution U4 to box U4 is equal to F4 is microlocalized, is a conormal vector to the vertical line, and that is microlocalized near nu of Z0. And I choose F5 so that it's just another compactly supported smooth guy localized near X. Now in this case, in the picture that you see here, Z0, or the point X, does not intersect the projected Lagrangian associated to U1 to 3. So there is no interaction between U4 and U1 to 3. So there's no observed singularity for U1 2, 3, 4, 5. So then Z0, Z1, Z2, Z3 does not belong to my 3-to-1 scattering map. However, if Z0 or X happens to lie on the projected Lagrangian, and the localized direction is chosen the right way, you're going to have U1, 2, 3, 4, 5 flowing out and hitting the world line of that observer, right? And then you are able to see the singularity in U1, 2, 3, 4, 5. So this is how you can use your PDE to characterize your 3-to-1 scattering relation. Right, so here's a proposed, I need to sort of jiggle this a little bit. This is not exactly what's right, but this is roughly the idea. Is that let's take Z1, Z2, Z0, 1, 2, and 3 be a 4 tuple. And so such that mu intersect the flow out of this special vector mu of the special Z mu is in the singular support of singular support of the pullback on mu of U1, 2, 3, 4, 5. And I'm going to take a closure of this. So we should be able to prove that this is indeed a 3-to-1 scattering map relation and a uniquely characterized by the source to solution map. So this is still ongoing process. But this ought to work. All right, and I think I'm 1 minute over time, but I think I was owed a minute because there was some internet connection, so I'll stop here.
Yeah, no worries. Thank you very much, Leo. And any questions or comments? Please unmute yourself and just speak. Any questions, comments?
Yes, one comment. This is very interesting construction, these microlocal mirrors, because you manipulate the measurement just by using the nonlinear medium. So that, for instance, like in adaptive optics that they use in telescopes, they want to focus observed signals to for the focal point. One would guess that maybe your microlocal mirrors would be considered as adaptive optics that has no moving components, that you are using a nonlinear medium and some fixed background field to focus the incoming wave. So it is a very interesting invention.
Thanks.
Any further comments or questions?
So this is a more technical question. In this kind of things, often geodesics that have loops cause some technical difficulties. That when you are proving the results, you know that it's very, very rare that the signal that comes to your measurement point, it continues and then returns back. So you have basically in Riemannian metric, you would have a geodesic loop that the light ray that you measure arrives to the measurement point several times. So is this causing any problems for you in the proofs?
So in the proofs, so you need to first argue that so I have two metrics and two Riemannian manifolds. You need to argue that if one loops back, the other one must loop back as well. And then you somehow rule those out. And remember that you're only always looking at minimizing geodesics between 2 points. And you can always perturb them to be strictly minimizing, so you're very safely within you're still minimizing even if you extend a little bit, right? And so within then if you only consider this type of regime, which you're always allowed to, then the ones that loop back won't have time to do it before this broken one comes back, right? The broken one always comes back faster than the one that loops, because if you only look at geodesic, which can be extended and still be minimizing, it must take more time for it to loop back, if it loops back at all. So that's how you can rule them out.
Any questions? Yeah.
Yeah, I have one. So have you thought whether you can use this for lower order terms? Whether you can get the lower order terms just with one single measurement?
Yes, of course. So all these things can be, so everything that has, I think this is robust enough to adapt to most things that we have done already by simply using this mirror, right? So as long as you're able to make an observation at that single point by using this extra reflection, right? You can actually, so as in your case, I think you're thinking about recovering the connection, for example.
Yeah, right. So that will take you to a problem which is a little bit more challenging to solve than the distance function, I guess.
Right, but then you're still able to, so remember that you are still able to compute the symbol of these things along these Lagrangians, and then at the end you can somehow still, so if you have something that reflects back and then you're able to compute the symbol of that, then you're probably able to work backwards to see what the symbol was where it reflected. Right, I mean, of course, I'm just speculating here. I'm just it might not be a satisfactory, it may not work out, but that's what I'm thinking, is that you can work yourself way back to what the symbol was when you reflected. And then you have exactly the data that you had.
Yeah, that makes sense.
Yeah. Any further questions or comments? So if no, and let's thank the speaker again. And so we will come back at 3.